IR Dr. Malathy Batumalay. So, a short introduction about myself. I'm attached to INTI International University. I obtained my PhD from University Malaya, Malaysia. Currently, my research is on photonics engineering. I'm a chartered engineer of IET, a professional engineer of Board of Engineering Malaysia, and a professional technology from the Malaysian Board of Technologies. Whatever research that I'm attached to, I always ensure that my research is aligned with the Sustainable Development Goal, collaborates on innovation, technology, and education. This research work is under the umbrella topic of sustainable development. The SDG is a goal commitment towards a more sustainable, resilient, and inclusive development. The insight, opinion, and visionary thinking generates ideas. Ideas forward through collaborative partnership, and these are enabled to contribute to the requirement of the industry. So, a short introduction about telecommunication. In telecommunication, transmission is the process of sending and propagating an analog or digital information signal over physical point-to-point or point-to-multipoint transmission, which could be in the format of wired or wireless. One example of transmission is the sending of signal with limited duration. For example, blocks or packets of data or even a phone call and through an email. So using an optical fiber, which is flexible, transparent, we are able to draw glass or plastic to a diameter slightly thicker than a human hair. Optical fibers are used most often as a mean of transmit light between two ends of fiber, and it is fine wide usage in fiber optic communication. An optical fiber cable is a cable containing one or more optical fiber that are used to carry light. The optical fiber elements are typically coated with a plastic layer containing a protective tube suitable for the environment where the cable can be deployed. So this optical fiber consists of a core and a cladding, which you will see in the next diagram. So optical fiber typically includes core surrounded by a transparent cladding material with a lower index of refraction. Light is kept into the core by the phenomena called total internal reflection, which causes the fiber to act as a waveguide. And this enable low loss, which is important in fiber optic communication. So definitely we are aware that fiber optic is definitely versus from copper cable, and it is enabled to give a lot of advantages over the copper cable. The advantage of fiber optics can be seen where it gives us a higher bandwidth capacity where light can travel further without the need of signal boost. There are less recipients to interference such as electromagnetic, and they can be submerged in water. These fiber optic cables are stronger, thinner, and lighter compared to copper cable, and they do not need to be maintained or replaced frequently. So, in my research work, evanescent waves are formed when wave traveling in a medium undergoes a condition called total internal reflection. This was the point that triggered me to do this research. So, in my previous work, the total amount of evanescent wave is directly proportional with the reflection of light. Measurement is based on modulation of light, and to enhance the performance of this fiber, zinc oxide provides a higher surface to volume ratio was used to absorb more water that changes the reflective index, and indirectly this fiber was working as a humidity sensor. Today, we are focusing on fiber optic sensor, which is working as a SPR, surface plasma resonance sensor, which is now being utilized to detect the changes of refractive index. Therefore, the mass density in accordance with molecular association, or you can see the reaction on the surface of thin metal layer. SPR is enabled to detect the refractive index changes, and with the deployment of nanoparticle together with the SPR is widely used in sensing. So we can see what is the reason of this device working as a unique optical properties, it's because of the deployment of nanoparticle on SPR. These nanoparticles are able to absorb and scatter light with extraordinary efficiency. The interaction between the photons and the electron, which is coming from the metal, is enabled to work as a collective oscillation at a specific wavelength. Indirectly, optical fiber can be used as a sensor to measure strain, temperature, pressure, and others. So today, plasmonic sensors are widely used for glucose monitoring, environmental monitoring, disease detection, telemedicine, chemical sensing, lab on chips, medical diagnostics, and also for bioimaging. So my ongoing research works is focusing more on plasmonic sensors for relative humidity. We have actually deployed graphene oxide, which I use as a selective layer for the relative humidity detection. It works together with gold-coated setup, which shows a stable response. On the other hand, the same type of sensors using prisms were used by actually deploying graphene and gold, which is coated on the SPR Crashman setup. And this development was used for sodium nitrate detection for food safety purposes. So again, the interaction of SPR here involve light energy coupling when interaction occur between photon, which is the light, and the electrons that is on the metal surface. Why gold? Because it is a plasmonic material that gives SPR signal at a convenient combination of reflectance, angle, and wavelength. Currently, we are also using the same setup using metal, which is coming from gold layer, and with the same reaction of SPR, we are able to perform studies on surface plasma resonance for gas sensing. And these optical sensors uses a setup called Crashman surface plasma resonance to detect hydrogen sulfide at room temperature. Now, moving forward, we are looking for machine learning algorithms for the surface plasma resonance where it is enabled for the biodetection application. All right, let's go into the introduction. As mentioned earlier, SPR sensors have many applications in detecting toxic gases, water pollutants, and biomarkers for many diseases. These SPR sensors are good candidate for the future sensing platform due to their high sensitivity and fine resolution. However, the challenges of high cost, cross sensitivity, and large amount of generated data need to be addressed to unlock surface plasma resonance potential. Therefore, we moved into machine learning algorithms which can address these challenges. In this short review, recent studies integrating the algorithm of artificial intelligence and machine learning with the SPR sensing mechanism for biodetection applications are presented in this paper. The short review shows how the integration approach can help to face some of the challenges that we are facing. Looking at the principle, the surface plasma resonance is a coupling of photon energy with the plasmons of the metal dielectric surface. Surface plasma resonance occurs due to the coherent oscillation of electrons in the metal dielectric interface of a high refractive index dielectric media coated with a thin layer of metal which is coming from gold, silver, and aluminum. This is a kind of nanostructure material which are sensitive to light energy. The propagation constant of the plasmons is as followed in the equation that is given, and the second equation shows the propagation constant of this algorithm. SPR methods for biodetection application is presented where the wavelength interrogation is locating the wavelength at which SPR occurs. SPR sensors have a selective coating of plasmonic metal layer, and when the analyte binds with the selective layer, the refractive index of the metal dielectric layer increases. Therefore, resonance dip experiences a shift. Those wavelength dip shift with the presence of analyte are then mapped with the sensogram, which are simple resonance curve that can be made readable to the state where the analyte presence and the sensitive sensing process kinetic is detected. The angle is a similar process that uses monochromatic light source, and the resonance angle is one of the experience of shift in the analyte presence. SPR has been used to build dengue fever sensors, for example, using Crashman SPR sensor that I have demonstrated earlier. And it is able to give a performance with the sensitivity of 0.2576 degree, and it is within the range of 0.08 to 0.5 pm. Another SPR sensor used a tapered fiber functionalized with the dengue fever antibodies as well, which shows a sensitivity of 5.02 nanometer with the detection time of 15 minutes. So this SPR sensors is suitable for biodetection application. SPR instrument can be bulky and expensive. These standard sensing signal are resonance angle, reflection intensity, resonance wavelength, and can also work on phase changes. The angle and wavelength resonance changes are most common signal. This method need expensive spectrometer and rotating stage. And these rotating stages are actually need to be aligned with each other during the experimental setup. Further work is needed to make this method more cost effective. Therefore, using the machine learning algorithms can help extract readable signal even in poor signal to noise ratio, which is enabled to reduce the cost of building SPR setup. So, to enhance sensors with machine learning, smart devices are built on sensors and artificial intelligence softwares are incorporated in factories, hospitals, and even houses. The breakthrough in AI and machine learning technology, together with big data storage capabilities and cloud computing help, makes AI-powered devices, which is possible using Siri, Alexa, and also Google Home. Conventional machine learning algorithms select individual features to achieve the desired performance level. Using deep neural network, it is enabled to generate the features automatically during the learning process, and these DNN algorithms are performing well in image and speech recognition. Looking forward, smart machine learning backed sensors can be used to automated monitoring, predictive maintenance, and fault detection. Additionally, machine learning algorithm can be used to integrate simulation data from computational simulation with the collected data from sensor to predict complex system behavior. Using scientific machine learning is used to build virtual sensors to monitor parameters that cannot be measured directly by developing collaborative behavior from the available working sensors. Machine learning can help to improve SPR biosensors because machine learning algorithm improve the performance and development in a more cost-effective sensors. Indirectly, machine learning process large amount of data during the angle of wavelength integration to obtain reflectance curve. Machine learning algorithm also extract sensing signal from noisy sources. Thus, the light source with lower power can be used, which can be safer and cost effective. Cross sensitivity to ambient environments such as temperature, humidity, and pressure can hinder SPR sensors. Machine learning process this variant and build multi-parameter sensor that consider the ambient environment. The dynamic response of SPR sensors shows non-linear behavior where it is able to interact with the surrounding or the analyte. Machine learning algorithm use the sensor data if some output data is independent of this transition and also drift. Recently, machine learning algorithms were used to optimize the coating of plasmonic material, processing the sensogram and other sensing data in surface plasmon resonance. So machine learning was used to guide the selection of seed-mediated growth to get the desired plasmonic wavelength for gold nanoparticles called SGNPs using genetic algorithm-based artificial neural network. Machine learning has been used to improve the performance of SPR sensor even for DNA detection. The reflectance characteristics of metamaterial were predicted using autoencoder AE with the multi-layer perception MLP. Clustering facilitated an accelerated design process, and this sensor improved 13 times in terms of detection sensitivity over the conventional SPR biosensor. So a plasmonic or SPR sensor for SARS COVID virus particles establish a regression machine learning model to predict the virus concentration. On the other hand, a plastic cladding silica fiber sensor was used to build the biosensor where VIS and NIR CMOS detector captured the transmitted spot image. Using Crashman-based SPR imaging setup was used to detect multiple biomarkers in undiluted whole serum samples. Despite its potential to improve SPR biosensor performance, machine learning in sensors design still faces some challenges. Few more publicly available datasets can be used to train the machine learning algorithm. Therefore, SPR sensor design need to improve for standardization to be used for machine learning training. Many published SPR sensor method differs widely from each other. A global framework for these machine learning powered SPR biosensors need to be considered to facilitate the adoption of machine learning algorithm. Regardless, even for individual SPR sensing setup, machine learning can be a great use in saving processing time and cutting high costs. So in conclusion, machine learning can enhance SPR biosensors performance by helping to sort the output signal, detect and reduce effect of noise, automate the sensing process. ML algorithm were used to process the sensogram and reflectance curve of SPR sensors, and this algorithm were used to process endpoint images collected by SPR system. The use of machine language algorithm in SPR biosensors showed improvement in sensitivity and reliability. I believe this is the next direction of sensing. Thank you very much.